Hi, welcome back to Riemann sums and area under a curve. We're really going to focus a lot in this course about something we call area under a curve. Calculus basically solves two questions. One, how fast am I going? And the second question that we like to ask ourselves is, how far did I go? Well, the first question, we answered that earlier with derivatives. To answer how far we go, we use something that we call a definite integral. And we're going to talk a lot about that today and tomorrow, so hopefully this will make a little bit more sense. If it doesn't make sense today, by tomorrow it should be pretty solid for you. So that's the second question we're going to answer for calculus. If we let f, and here's how we solve it, if f be a function, I feel like let f be a function over the domain a to b, then the area under the curve is defined to be the integral from a to b of f of x dx. This equation right here is so very important for us because what this finds for us is area under a curve, and we're going to prove that in just a few moments. We call this a definite integral, and here's how we get area from an integral. So we talked in part 1 about how we find area using those Riemann sums. How we get the area is just kind of the same way. If I think of this as just one gigantic rectangle right here from A to B, I can use my Riemann sum to get this. I know the height is f of x. The base is my change in x. B minus a is my change in x. Remember, this is just my b minus a. And here is my length, and there's my width. So to get the area of my rectangle, we're going to take length times width, or f of x dx. But let's have fun. Recall that delta x, we need 2 points. That's my change in x. That's like my average rate of change. We want dx. In other words, we need 1 point. And we're going to talk more about this tomorrow, but it's basically this. We're going to use limits. If we let delta x go to 0, we go from needing 2 points. If I let this distance go to 0, we go from needing 2 points down to 1 point. And this is kind of the rule, and we're going to talk about this in the future video. If we let delta x go to 0, we get dx. It's pretty simple. I mean, think about it. If I let delta x go to 0, this distance between becomes 0, which means we're at 1 point. And therefore, our area then becomes f of x dx. And then now remember, this is the area. What this becomes is the area of an infinitely thin rectangle. An infinitely thin rectangle. Basically, its width approaches 0. Okay? And we're going to add up a whole bunch of those. And that's how we get the area under a curve. Now, we're going to talk more about this tomorrow, so don't stress that right about now. But let's see how we can apply area under a curve. A car is traveling so that its speed never decreases during a 10-second interval. The speed at various times is listed on the given table. Use the table to explain why the best lower estimate. Now, look beforehand. Before we talked about right-hand. Whoops, sorry. Wrong page. Before we talked about right-hand limits and right-hand sums and left-hand sums. But this time we're using the phrase lower estimate. So we'll talk about that. There's upper, lower, right, left. These are all still considered Riemann sums. So we want to use the table to explain why the best lower estimate for the distance traveled in the first 2 seconds is 60 feet. So we're only looking between 0 and 2 seconds for question number part A. So we want to get the lower estimate. So if I graph this, the AP loves work. Between 0 and 2, I want to pick the lower estimate. Well, which one is the lower value? At between 0 and 2 seconds, which has a lower value? Is it the 30 or is it the 20 or the 36? Well, the 30 is my lower estimate. That's lower value. So I pick the 30. So what we're basically doing, we're pretending between 0 and 2 seconds, we're traveling the entire time at 30 feet per second. And that becomes a rectangle. Well, to get the area, remember, this is just from physics. This is my time, and this is my speed up here. I can say that my area, if I look in terms of rectangle, is speed times time. Or, in other words, in this case, speed, and this is basically delta t times delta t. So let's look at just the units alone. This is always good practice. Speed here is measured in feet per second, while time is measured, of course, in second. Those seconds cancel, and what we're left with is feet. So the area here is giving me feet units. So the area, in this case, is giving me distance. So what this tells me is that the area is the distance traveled in 2 seconds. Now, it's really the displacement. We'll talk about that more later on. But it's giving us how far we traveled from the original spot in 2 seconds. But it's really the displacement. We'll talk more about that later on, okay? So to get my area then, I'm just going to take the length of my rectangle, which is 30, times it by the width, which is 2, and we're going to get 60, the units, feet. And that's what we said. And that's why the lower estimate is 60 feet. Now we want to get the upper estimate. So I'm going to do the same thing. So to do the same thing between 0 and 2, but now we're going to pick the upper estimate, 36. So that means we're going to pretend like between 0 and 2 we travel 36 feet per second the whole time. Draw your rectangle. AP loves it. Because we want to see that the distance is 72 feet. Now for the lower estimate, remember, we picked the smaller value, the small value. But for upper estimate, we're going to pick the larger value. Excuse me. So my area, again, which is speed, remember, there's my delta t, change in time, times a change in time. Well, the speed is 36, and the time is 2 seconds, and that's 72. Now we already found out that it was feet above here, so it's 72 feet. Right there. Very easy to do. Now what we're going to do is we're going to use the table to give the best lower estimate and the best upper estimate for the distance traveled in the first 10 seconds. So now we're going to break this up. So now we're going to break it up into many different little parts here. So we're going to go ahead and do the lower estimate first. So draw out a table. I promise you this helps. So we want the lower value. So I'm going to break this down to my time units, 0, 2, 4, 6, 8, 10. 0, 2, 4, 6, 8, 10. Now you really want to make sure you pick the smaller value and draw out your rectangles. Between 0 and 2, the smaller value was 30. So I'm going to draw a rectangle at a height of 30. I tend to draw it right here. There's my first rectangle. Between 2 and 4, the lower value was 36. So I draw a rectangle of a height of 36. Not drawn the scale, but the AP likes to see this. They really want to see where you get your answer. If you just have an answer, the AP won't give you credit half the time. They want to see where you got your answer. And drawing out the rectangle, the beautiful way to do it. Between 4 and 6, 40 is my lower value, so I draw my 40 there. Between 6 and 8, we're looking at 48, and that's on the scale. And between 8 and 10, we're going to pick the 54. We're going to pick the 54, draw your rectangles, and now to get my area, remember, write out what your formula is. Area is speed times your change in time. Remember, this is going to give me distance right there. What is speed times time but distance? So we're saying that the area underneath this is distance. There's my time, right? And of course, there's speed. And I can calculate this. It doesn't take long. The first one is 30 by 2. Again, don't get into a habit of factoring out the 2, because here they're nicely separated out. A lot of times they're not. The next one has a height of 36 by 2 plus 40 by 2 plus 48 by 2 plus 54 by 2. Now you can leave your answer like this. You don't have to simplify. AP is okay if you don't. And this is going to be in feet. We know that because we got speed times time. Feet per second times second is feet. Now if you want to simplify this out, you get 416 feet. Right there. All right. To get the upper estimate, we're going to do the same thing, but this time we're going to pick the larger values. 0, 2, 4, 6, 8, 10. Between 0 and 2, 36 is my higher value. So there's 36. Between 2 and 4, 40 is my higher value. Between 4 and 6, we pick 48. Between 6 and 8, we pick 54. And between 8 and 10, of course, 60. And the same thing, get the area. Remember, speed times delta t. Don't assume that just because you wrote it once, the AP doesn't want to see it again. Always write it out. Speed is equal to, or area then would be 36 by 2 plus, this is 40 by 2 plus 48 by 2 plus 54 by 2 plus 60 by 2. And that's going to be feet. You don't have to simplify it. You just, there it is right there. And if you do simplify it, though, you do get 476 feet. Now, one thing that, what is this telling us? The lower estimate, remember, this is telling me what is the minimum distance that we travel. The minimum distance traveled. If the car is constantly speeding up, this is the least that we would go. What was the upper estimate? Well, this is giving us the maximum distance traveled. Minimum, maximum, sounds kind of familiar. We might see those words again later on. So how would this be pointed out in my class? Well, of course, you get 1 point for the graph, 1 point for your formula, 1 point for your answer. 1 point for your graph, 1 point for your formula, 1 point for your answer. So maybe we're like 3 points apiece. And they take less than a minute to solve these. All right, the last question says, if you choose the lower estimate for your approximation, what is the maximum amount your approximation could differ from the exact distance? Well, this is just basically like our error, right? That's our error stuff. What's the maximum we can do? Well, we can take the 476 minus the 416, and you get 60 feet. So what does this tell us? This is the most we could be off by. In other words, if I want to estimate how far I traveled in the first 10 seconds, the most I would be off between my lower and my upper estimates, I'll be off by at most 60 feet from the actual distance I traveled. Not too bad for an approximation technique. And that's what Riemann sums are. And that's what we just did right here. Okay? These are what we call Riemann sums right here. And what a Riemann sum does is it gives us an approximation of the area under a curve, and the area under the curve in this case gives us distance traveled. I hope you guys enjoyed the video. I will see you later. Bye-bye.